So we're here to talk about memory. So I used to do a lot of garbage collection talks, and then they got sort of boring, and I said, okay, what's next? And so I figured, there's two aspects to memory management within the JVM. One of them is actually the garbage collector cleaning up stuff, but then there's also the bits that make it messy. And the garbage collectors have actually been getting really, really good over the last couple of years, and we have some really nice options for it. To the point where we can tune the collectors so that basically you're not going to notice what's going on inside the JVM. We've done this for many, many, many sites across the planet. It's like from rail companies, banks, travel, industry, like pretty much you name it. So typically what we find is it's no longer really the garbage collectors that are the problem, because the garbage collectors will create what we call like these tail latency issues, because all of a sudden you get this pause and all of a sudden you get this like really massive tail latency problem. So if you get rid of that, that's one side of the problem. The other side of the problem is just how do we allocate in our applications? And surprisingly enough, how we can allocate is actually one of those really, really interesting problems to look at, especially in applications that you see day to day. So that's my marketing slide. So I co-founded this company called JClarity. So we have to be buzzword compliant. So what's the machine learning, AI? It's got to go in there. Right, okay. Sorry? Blockchain. Oh, damn, we didn't put blockchain in. Okay, so I got to figure out a way to get blockchain in there. Okay, so it would be, reactive, what else you want? Anyways, fully buzzword compliant tuning, application is a diagnostic engine. And so one of the things I've developed over the years is a methodology for performance tuning applications. And we actually managed to encode this into some sort of machine learning algorithm. Actually, what we're able to do is after a while is just strip away the machine learning and use some lighter mathematics for the problem. But anyways, it's been an interesting project, and we've actually had people pay for it. Silly people. Nope, sorry. I didn't say that. So it's been a very interesting ride doing that. And of course, JClarity, we say the hottest unconference on the planet. Okay, oops, something happened here. So another thing we actually do is I've had my team actually working on the Adopt OpenJDK project. Does anyone know about Adopt OpenJDK? 2, 3, 4, 5, 6, 7, 8, 9. I guess I should do the exercise first to see if the arms are working, right? Everybody arms up. Awesome. Okay, so the rest of you, we'll work out medical aid for you later. Okay. So really, what I want to do is I wanted to just briefly mention the 3 disruptive changes that we've seen in the Java ecosystem, and just to help us understand what's going on. First was JDK 9. So the first question I have is anybody here using JDK 9 Plus? Trying to? Yeah, okay. That's actually kind of fun. So there's a whole bunch of people and anyone still stuck in JDK 8? Oh yeah, 7? 6? 6, yes, lovely. 5? 4? 3? 2? 1.1.19 or less? I mean, we do have one customer who's 1.1.19. What? Yeah, it works. So, and they have no interest in changing. So, okay, whatever. So anyways, there's really 3 disruptive changes that came with JDK 9. So, there's a whole pile of things that just broke just about every tool that we could possibly imagine. And so, one of the complaints we've been having is okay, if you keep destroying our tooling chain, you're just going to make us go back and fix things that have been working for years. So I've spent a lot of time just fixing stuff that used to work. Of course, part of that is logging and how we get information out of the JVM. Has anyone noticed that all of a sudden we go from these wildly wacko iReadable logs to these uniformly formatted iReadable logs and stuff like that? Anyways, So we introduced unified logging, which part of it. And of course, the big daddy of them all, modularization, right? So 11, we managed to convince, well, up until 11, we managed to convince Oracle to turn it off by default till we figure out what it was going to break. And now they've turned it on. So if anyone's trying to move up to JDK 11, of course, you're now facing the module monster, which is always lots of fun. Then, on top of that, we had this minor change in the release cadence, right? Does anyone know what an LTS is? Right? Do you know, here, better yet, do you know what the LTS releases actually are? Yeah, it is 11, 17, 42. Yeah, it's got to be 42 in there somewhere. Right, so we have this, every 6 months now we get a new version of the JDK, which is really cool for the guys in Oracle because, as you look at JDK 13 was forked. By the way, we are actually using JDK 13 in production. Imagine that. And it was just forked, meaning that it's essentially getting in the process of being locked down for the release in September, right? And which is really cool because, they can just sort of like get a list of features and they say, yep, that one's ready, that one's ready, that one's ready, and they can roll them in. And if you happen not to be ready, so if anybody's been looking for like mmap, memory mapped, better mmap support, right? That got rolled out. So you're not going to see that in 13, but you'll probably see it in 14 as an example, right? So the release cadence really helps the guys in Oracle really not hold up releases so they can just release what's ready and go forward. But of course, on the receiving end, every time you receive a new version of the JVM, of course, to roll it into production, how easy is that? Typically it's, for some places, they might take a year to plan, which means that to roll in a new JDK, which means that there are 3 versions behind by the time they actually do this. Right, so, oops, I think these are my European slides, sorry. I'll have to clean them up for here. And of course, the big monster that just hit us is licensing. Does anyone actually understand the licensing issue? It's like, sorry? You tried to, yes. Yeah, my boss, which is we got a circular relationship because I'm also his boss. It's really fun. He wrote a paper somewhere. We have a link somewhere for it. Basically, trying to help explain what's going on. The documentation is so long in the explanation that I don't think anyone read it. So we tried to write one of those TLDR things, whatever they are. And that turned out to be too long for people to read also. So it was really kind of funny. Oh yeah, by the way, as of April, like not next, but last, use of Java 8 comes with commercial restrictions. So if you're using Oracle's version of JDK, then you really actually have a problem. Oh yeah, so actually no, it got published on Mediums. Like this, Java is still free, whatever free means. Right, so Oracle dumps everything into OpenJDK, and then they fork OpenJDK, so they make Oracle version of Java. Of course, now everybody and their uncle starts forking OpenJDK and creating their own branded version of the OpenJDK project, of which, of course, we had to jump on the bandwagon and create Adopt OpenJDK, which is part of the Adopt project. Now, so that was, the Adopt project was started inside the London Java community. And just recently, I just did a 2-week tour of Japan, where we went to speak to user groups, and Jay Onsen, which is like basically talking about Java in a hot tub, if you can imagine. Yeah, I know, crazy. And yeah, so I get this really nice, cool t-shirt there. See, Vincent picked the color I should pick out here. It's really nice. So we actually, in talking to the Tokyo Jug people, drew them into the project, and have since been talking to the Sao Paulo people, and we've drawn them into the project. And now we're looking at basically drawing from a pool of about 70,000 Java developers to help us with this particular project in terms of creating a community around it. So we will be looking to draw other user groups into the project to try to sort of fluff that number up to make it sound even more impressive than it really is. But essentially, what we're trying to do is actually build a truly open and free version of Java that everyone can trust and they can download. And it looks like some governments are going to get involved. So like the Dutch government is very interested in this project as one example. And there's a couple of others that are also interested in helping set up what they call commercialized public infrastructure, for companies in their country. The long and short of it is that, officially Java is forked. The project is basically forked at this point in time. I mean, it's actually been forked for quite some time, but it's just people haven't realized it because the forks have not generally been available. But now you're starting to see people like, just this morning, Alibaba came in and said, we got this big change that we'd like to push on G1 memory management stuff. And so what you're seeing is the forks coming from Twitter and coming from places like Alibaba, Goldman Sachs, and a lot of other companies that have their own internal JVM teams actually being pushed back into OpenJDK, right? And so that's trying to minimize the forks. But what we still have is a compatibility test suite problem across the entire platform. So if you get from adopt, how do you know that this is compliant with Java that you might get from Azul, for example? And it becomes a tricky question because now, everybody's in the business of backporting patches. So just this morning, we had a silly conversation about how we might backport ZGC patches into like Java 9 or 11 or something like that, right? Because you don't really want to use ZGC. I think even in JDK 13, I probably wouldn't use it in a production environment, although I'd start looking at how you might want to use it. Right? So there's all of this stuff happening now, and so the question is like, how do you ensure that you get consistent behavior across JVMs? And it goes down into like really strange things. Like, does anyone know how soft references actually work? Great. I was hoping someone could explain it to me. But, because there is no real spec for how a soft reference works inside the JVM, and they work differently in different JVM implementations depending on how they're patched or which garbage collectors you use, how they're implemented, because, the net result is that your memory footprint is going to be quite a bit different depending upon which implementation you use, right? Does anyone use any caching? Silly question, right? Right, so, that's where you're going to find the soft references in the caches. So even if you don't realize you're using them, you're actually using them. So there's just some really funky things going on here, right? So I'm going to say that Adopt is the only community-driven distribution on the planet today, which is why we wanted to go off and support it. We've just accepted a push of like approximately 100,000 tests. The 25 million downloads is actually old information. It's more like about 50 million downloads of this particular project right now. Multi-vendor backed, so there's a lot of different vendors that are involved in here. Pivotal should be on there, and a few others on the list, right? So everything is open, transparent, and free. And if you want to contribute yourself, then of course you're all welcome to join in on the party of continuing the march toward forks. I think what you're going to see, hopefully within the next year, is that there will be a foundation around this particular project as a way of normalizing contributions from different companies and things like that. So this is something that's in discussions as we speak. Right. Any questions on that before we move forward? Just say that there is really a lot of disruptive changes happening in Java right now, which when you put them all together has made a lot of people very nervous about what's going on. But I think that, quite frankly, the future looks very good. We had the Jakarta incident, which I don't know if you're aware of, where JEE was, does anyone care about JEE? Sorry, does anyone use JEE at all? Yeah, a little bit. So probably not as much interest, right? So if you use Tomcat, anyone using Tomcat or something similar? Yeah, okay, so you guys actually care, even though you didn't know it. So the JEE spec has been frozen mostly because what has happened is that JEE was like dumped into the Eclipse Foundation, but now they don't have the right to modify anything within Java X. Right, so if your eyes just got big, yeah, okay. So right now the Jakarta guys are sort of figuring out, okay, how can we create a shim to fix this until we can actually fix this so that people can actually start migrating forward without having to recompile things that they no longer have the source code to, right? So that type of issue. So those things are actually in the works. So it's really kind of funny what Oracle did there. They actually donated the project without donating the IP. I don't know. What can I say? Okay. So I'm going to ask a question here. Does anyone understand where their most common performance trouble spots are in their applications? Shout it out. Oracle database. Yeah, okay, of course. Love them things. Any other suggestions? Just shout them out. No? Nobody has performance problems. What do you have a performance talk for if you don't have any performance issues? Okay. Startup time is an issue. That's a whole other talk. What do you mean by startup time? JVM starts up plenty fast. I have no idea. I mean, if you look at the benchmarks about startup time, you just want to pull your hair out and they're really, really bad. I mean, in Japan, I saw a benchmark given in a keynote that we looked at it afterwards and we said, okay, you just can't write benchmarks this way. Again, that's another different talk, which I don't want to go. But I haven't seen a benchmark on startup time that I actually believe or trust at this point in time. They're all pretty much broken in some ways. Okay, anyways, back on track, otherwise we'll never finish. So here's a chart that was made by a good friend of ours, Simon Maple. I'll name him because he should be proud of this chart. It's really good. They surveyed tons of their customers, and they made this really nice bubble chart that says, hey, you're right. The database is the problem, right? Unfortunately, this chart is what I call my poster child. This is my go-to poster child for what is wrong with observability in our systems today. Okay? This is an example of what I call street light performance tuning. Has anyone heard this expression before? It's really, really kind of a fun one. So, you drop your keys in the dark. Where do you start looking first? Where the light is, of course. And really, this is a reflection not of where the performance problems actually are, but it's a reflection of how good things are being monitored. That's what that is. Because when we actually look at the right data, and this is like one of these things that, like as they say, once you see this, you can't stop seeing it. You really can't see it. It's excessive memory churn. That little tiny small dot up there, right? If you look at that, right? This is what we find. It's in greater than 70% of all of the applications that we get data for. And we get data from a ton of applications. I tend to tune somewhere in the neighborhood of 2,000 to 3,000 different JVMs a year for garbage collection. So I've been doing that consistently for a number of years. So this is a problem that you just keeps coming at you, right? And I like to say, so it's a memory problem, and no, the garbage collector is not at fault. This is your fault, not the garbage collector. You can't really blame it on a garbage collector. Oh, and by the way, we had some comment on C++ or whatever like that during the keynote. Does anyone have an idea of how much time you would spend in memory management in a C++ application? Any guess? Wild guess? pretty close. It's somewhere around 60%. The LDAP guys, when they were tuning it, they found initially when they started tuning applications, 60% of their code base was actually in memory management, which is generally way more than what you see in a Java application. Anyways. So the question I have, do you use Spring Boot? Yeah, lovely. Cassandra, it's probably an older one. Or, what does it say? Any big NoSQL solution? Yeah, Spark, things like that. We actually talked to the Spark guys last October. They were over there until I had a nice chat with them, so hopefully they're moving in this direction. Right, Apache Spark, yeah, whatever. Log4j. Log4j is my favorite one, right? That's a whole other talk onto its own. It's like if there's one framework I could rid the planet of, and I think we'd be all better off for it. I mean, that would basically cover my carbon footprint for the rest of my life. It's got to be Log4j. Seriously, it's seriously bad. Or any other Java logging framework. So in our projects, we actually use the Java JDK logging framework, not because it's any good. It sucks, but it sucks just as badly as anything else. So, and we don't do much logging anyways, because logging is, passé. JSON? Anybody using JSON? All right, who's not using JSON? Yeah, JSON's very bad. It messes with a whole bunch of different things. And quite frankly, I don't think many computers really care if they can read the format of your data or not. Like, if humans at the other end, it's a weird thing. With almost any marshalling protocol, we find that this is a problem. Ecom, caching products, Hibernate, and so on, and so on, and so on. So I think that pretty much I must have hit on frameworks that most of you are using, if not one, at least multiples of these things. And I say that if you're actually using any of these frameworks, then these frameworks are just notorious for just churning through tons of memory. Yeah? And these things really hurt. It's really funny. It's like around Christmas time, we had a nice conversation with the .NET people. Yeah, I know it's like the dark side guys. And guess what their number one problem is? At least these guys are really clever. Guess what the number one problem is that they're facing? Allocations in memory churn. So they have the exact same problem, right? So here's some wonderful war stories. My favorite one is like we took a framework and we bumped it from 400,000 TPS to 25 million TPS. That took 4 hours. 4 hours. Not kidding you, right? I mean, I had like that companies, I had their best developer with me. So like it wasn't me, I was just pointing and going, and he went off and did wonderful things with the whole thing. It's absolutely crazy. I mean, we basically had this application running at the speed of hardware because we're able to get rid of the memory churn out of the whole thing. And there's just other stories like this. And it's like, why are we not seeing this? Why do we not see this? What's missing here? Well, the problem is like if you're going to use a profiler, you might find, like if you use an execution profiler, it's very unlikely you're going to see this with an execution profiler. So these guys here, they're very clever. I mean, they're not stupid. They used the execution profiler, and they kept using it, and so they got it like all the way up to like 400,000 by using the execution profiler. The problem is that the allocation problem doesn't really readily show itself in an execution profiler. The other thing too is it tends to be evenly distributed across your application, right? So it's sort of like the tide. So it's like instead of being there, it's up here. And since it's even, you don't have a differential in the signal to pick up on. If you don't have a differential in the signal to pick up on, then it's just very, very hard to see. So it's like things go slow and you don't know why. So you get into that type of scenario. Okay, so let's take a look at what's going on. And let's see how we can make it visible to you And once we've made it visible to you, then show you some of the hiccups that we run into. And then afterwards, the solutions. With any performance tuning problem, I look at it this way, right? You have two things you have to deal with. First is the diagnostics, and the other thing is then the clever thinking about things so that you can come up with some innovative solution to solve the problem. So here I just want to focus on the diagnostic because you guys I know are all very clever and you can come up with all kinds of creative, innovative ways of solving things. So most developers can do that very easily. The problems they have is in the diagnostics. So let's take a look at that. Okay, so here we have an allocator. So we get some Java code up there and we're going to create a new foo thing. And of course there's the bytecode for the new foo thing. And this thing forms what's known as an allocation site in your code. Allocations will occur mostly in Java heap, and sometimes they don't. They may not occur in Java heap when they're small, and they be optimized to actually be allocated on the stack. So I'll show you an example of that as we move forward. Other than that, we have what are known as fast path and slow path allocations, and I'll run through that very quickly. So Java heap itself is sort of divided up this way. We have a nursery, we have some survivor space, and we have some tenured space. So our allocators are going to allocate in Eden space, and over time, the data will be copied into the other spaces by the garbage collection threads. So tenured is to hold long-term data. Eden is to hold that's where everything is actually all created. So the fun thing is that each of these different spaces actually contributes to a different set of problems. So really what we want to look is what's happening in Eden, but we'll take a quick look at what happens with tenured also. So with Eden allocations, as you can imagine, there's a top of heap pointer, and there's some code. So we can say as we execute this code, the allocators are going to come along and they're going to decide, okay, I'm going to allocate a foo, which basically means I'm just going to do this bump and run on this pointer, which is at top of heap. And you can see basically as things get executed, we're going to get things laid out in memory like that. So in multi-threaded applications, of course, this is going to be a problem because we're going to have a hot pointer. So what happens is that in Eden, we're going to have these things known as thread local allocation blocks. So that means that every time a thread starts and it starts allocating, it's going to go to the heap. It's going to say, okay, give me a meg, a space. And I'm going to allocate into that mega space. And when I finished my TLab, then I'm just going to ask for another one. And when we run the garbage collector, we'll do some calculations. We'll figure out the hot allocators. We'll give them bigger TLabs. We'll figure out the cold allocators. We'll give them smaller TLabs. And so the TLab sizes will adapt from that point forward. Right, so that's basically how it works. Right, so you look at thread 1, it's allocating in its TLab, and thread 2 will be allocating in its TLab. If you have something bigger than a TLab, then of course you're going to go out into global heap and allocate it. So for example, this byte array will be allocated out in global heap. And that looks like it should be a slower allocation, but in fact it probably isn't because as you can imagine, when I finish the allocation, I'm going to have to run through some sort of barrier in order to basically resync all of the caches and publish or expose the data to all of the other threads so it has visibility to whomever needs it, if anyone needs it. We also have this other thing which we call a TLab waste percent. So that's going to be some threshold, after which, if we've gone past that threshold and we haven't overrun the buffer, then that's going to be the trigger to say, go get a new TLab. Okay? And of course, if we haven't quite hit that threshold, we might try to allocate there and it'll say, well, we're beyond the ends of the buffer, so now we're going to have to do a bit of rollback, get the other TLab. So this is sort of an expensive failure path. So we failed to allocate because we haven't hit the TLab threshold. Unfortunately, we don't really have any statistics to tell us how we might better set this percentage, but it can make a difference. We've experimented with some applications. You can get like a 3, 4, 5% speed up in performance in your application by adjusting these values to get better fit in the T-labs. In tenured space, I'm going to stick to the generational collectors. With the generational collectors, we're actually going to be using a free list. For those of you who are you now in 9+ are probably using G1 GC. So G1 GC is sort of going to work like how Eden works, with some twists. But that effectively what's going to happen with the parallel collectors and the mostly concurrent mark sweep collectors. We're going to end up dealing with this free list. And so as data survives the garbage collection threads will allocate them into tenured space. The garbage collector threads will be asking for what's known as P labs, which are promotion local allocation blocks. So 1 meg. So it's about the same mechanism to try to make sure that we don't have hot locks. So data in tenured should be long-lived. And the amount of data in tenured is going to affect GC pause times. So this is the whole thing where we say that, well, there's a couple of costs here. One is free list maintenance and scanning free lists and things like that. So you can see the scan is obviously, the cost can be linear to the size of the free list. So if we get like a really big tenured space, and then of course, we could be in a position where the scan of the free list is actually the dominating cost in our collection. Well, I don't want to say too much more about it, except for in terms of allocation. Allocating here is not cheap. This is a slow path, and it's about 10x the cost of a fast path allocation. Okay? Okay. So what are the problems we run into? Well, so I mentioned high memory churn rates as being a problem, which means that we have many temporal objects. Now, we've been taught for the last umpteen years by all of the garbage collection guys that collecting an object is cheap when it's in young generational space. Actually, it's free. And it is free to collect it, but it isn't free to allocate it, right? It still costs you to allocate it. Okay, so with the high memory churn rates, basically we're just doing a lot of allocations in memory, and the problems we're going to run here is that we're going to quickly fill Eden, which means that we're going to have more frequent young generational collection cycles, at a fixed pool size. Speeds up the aging. Now, what I mean by aging is that every time a piece of data survives a garbage collection, it's going to be aged by 1, and by the time it hits, I'm just going to say 15. I'm lying to you, but we'll just leave it at that for now. When it hits age 15, that's when it goes into tenured space. So if I have more frequent collections, that means that the data ages faster, which means that it ends up in tenured space faster. So you might say, okay, who cares? Big deal. Okay, here's the deal. We have this other completely dissociated situation or disconnected situation where we have a lifetime that our data is going to live in our system. And that's going to be generally generated by the business logic, right? The business logic might keep the data alive for 20 seconds. Now the question becomes, am I going to hit 15 collections within 20 seconds? Because if I do, that stuff's going into tenured. And if I don't, it's not. And if it's not, it's free. And if it goes into tenured, then I have another problem that I'm going to create in tenured space. Does that make sense? So we sort of have these two different aging systems basically acting on each other, which is kind of funky. Creates all kinds of different issues. It creates this issue which we call, so we have this other issue which I'll talk about, which is like premature promotion. So if we have a high churn rate, or we have a lot of data going in, then we get more frequent collections. That tends to fill the survivor spaces, and that gives us like another chance to catch data that should not end up in tenured space. And if we overfill that, then we actually have to tenure early, which means that instead of tenuring at age 15, we might have to tenure at age 10 or 5 or even 1. So that means things are going directly from Eden into tenured space. Now, why do we care about that? Is because by the time we go to collect tenured, that's going to be an exceptionally expensive operation. Right? That's our full GC, big pause times. I was just looking at a log this morning. They had 200 millisecond young generational collection pause times, which is really sucky. We'll fix that for them. But that was really fantastic compared to their full GC pause times, which are running about somewhere between 4 to 6 seconds. Yeah, right, exactly. Right, now we get increased copy costs because of the aging. We get increased heap fragmentation, which means that we get increased compaction happening. And, so the problems just come one after the other. So I'm going to say the allocation is quick, but still quick times a large number equals slow, right? So, each of these collections only happens in like just 4 instructions or something like that. So it's really, really cheap. 4 instructions and a barrier. As they say, you can fill a water tower 1 tablespoon at a time. You just have to go really fast to fill it quick. Right? Okay. So let's look at thresholds here. So this is going to be some magic chart wizardry here. I have no scientific basis for this except for our machine learning algorithms confirmed it as being true. And of course, we all trust that stuff, right? Hence the site spurious correlation. Okay. So what do we see here is like this chart. And basically the red zone means that you're hot allocating. The green zone says you're not hot allocating. And you can see the opportunity for performance improvements is really going to be this curve that looks approximately like this. And so you can see by the time we get down to around 300 megabytes per second in terms of an allocation rate, we're pretty much done. We're not going to get much more improvements in performance. But if you go above 1 gigabyte per second, then that's a target. And this is a target that actually, if you look at our 25 million, we went from 1.8 gigs per second to 0. I like the 0 part, right? But before we actually got to 0, we were still, in the tens of millions of transactions per second, right? And most of the largest gain coming from like 1.8 down to like about 500 megabytes in that range. Yeah. So this is really the opportunity that you're looking for. It's like, okay, if I have hot allocating applications, right, I want to find the hot allocation sites and see what I can do to eliminate them some way so that I can actually reduce the overall allocation rate to somewhere in that band, yellow to green. And that'll give you, generally in our estimation, minimally like 4x performance improvements. And sometimes we get greater, right? So, I mean, you've seen this, this is sort of like the theory of constraints coming into play here, right? You're going to have a bottleneck, and what they're saying is if you're tuning before the bottleneck, your application should run slower because you're just putting more pressure on the bottleneck. If you tune past the bottleneck, then you might get like a 5 or 10% improvement in performance. But if you tune at the bottleneck, that's when you're going to see the 100%, 10x, 2x, 4x, 5x, like type improvements in performance. So you really want to try to figure out where the bottleneck is and aim there. And if memory is your bottleneck, this 4x is a very common performance improvement we get in terms of transactional throughput. Next, I'm going to talk about a little bit about tenured, right? So live data set sizes, inflated data set sizes, and what we call object loitering. Generally, this tends to be data that ended up in tenured that shouldn't have been there. First off, if you're promoting prematurely or you're putting a lot of pressure on tenured space, you're going to end up with more frequent full GCs. Those are the things that you want to avoid. Even if you're using G1, where you have like a concurrent mark happening in the G1 space, even if you're using ZGC, which really isn't generational, or Shenandoah, which is not generational, we're going to still say that these are issues because they're going to go through these marking phases that are just going to take longer and longer and longer because more data is just, there's just absolutely more data to deal with. So we get inflated scan times, scan for root times. So when I start a garbage collection, I have to first find the things that I know to be live by definition, GC roots. And then I'm going to start tracing all of the live objects from there. This is why why dead objects don't cost you anything is because they're not reachable from a GC route. So I don't visit them, I don't mark them, I don't sweep them, I don't do anything with them. I just copy out of the space and then I just reuse the buffer. Right? I get reduced page locality. Okay, well, so that's kind of a funky thing. So if we look at reduced page locality, what are we saying? It's like, okay, so we have a memory system that basically pages things. And if I put data that's related and I'm going to access on the same page, then that means I have to use less hardware in order to do address lookups to find things. And without getting too deep into this, right, if I have to go across pages, then quite frankly what I'm doing is I'm relying on different buffers within the CPU in order to actually help me map the virtual addresses to the real addresses, make sure all of the pages that I need are in memory, and then do the actual, fetch the data activity, right? So that activity just becomes just like more expensive. We get inflated compaction times because it just becomes more difficult to compact data. You think of trying to defrag a full Windows disk as opposed to defragging one that's almost empty. As an example that you might have experienced in your life. So there's all of these different issues. And so if we look at these two charts here, the chart on the left is actually, you see, just forget about all of the massive junky stuff going on. Just look at the red line, the red thing at the bottom, and imagine that being a line. Okay? So everything under it is basically representing the amount of live data that's in this Java heap at any point in time. And if you look at this chart over here on the right, that's pause times. You notice the correlation between the pause times and the heap occupancy, right? So this is all, and actually this is heap occupancy, well, it's of all heap, but mostly it's going to be heap occupancy of tenure that's actually going to affect that problem. So you can see more data, more work for the garbage collector to do, more work for the garbage collector to do, longer pause times. Simple as that. Okay? So, moral of the story, don't keep data. Right. Exactly. We're done, right? And of course, our third problem is unstable live data set size, and that's actually another talk. It's about memory leaks, and eventually you run out of heap space, you get out of memory errors thrown, and your JVM will shut down and terminate if you're lucky. If you're not so lucky, then you have to do some other things. Finally, before we get into demos, I'm going to talk about this little thing here called escape analysis. Okay, so this gets into a little bit about JIT compilation, and I don't really want to get too deeply into JIT compilation except for to say that you have these profilers in the runtime and they're looking at your code, and eventually what they'll do is they'll take your bytecode and they'll just compile it into machine code. And some of the things they're looking for, or one of the things they're looking for, is the scope of your data. In other words, they were going to look at all the data access and they say, or how the data is being allocated, and they're going to say, is it possible that any other thread can actually see this piece of data? And if the answer is no, then we can do all kinds of optimizations with that data. There's all kinds of things that we can actually do, okay? And if the answer is yes, then of course the number of optimizations we have available to us actually starts declining. So moral of the story is when you're writing your code, the more locally you scope your variables, the better the JVM is going to treat things. If you're using statics and things like that, then that has global scope, which means that you have great visibility, which means that the compiler's ability to optimize is generally reduced. Okay? And it turns out that escape analysis itself is not quite so wonderful. So for instance, it might be the case where you just make a method call and you call into that method with this piece of data or this reference to this object, and then you just return. And everything's in a local scope. And you just hope that all works, right? So that it passes escape analysis. Wrong. It's not going to pass escape analysis because you've used it in a method call, and so it's going to be considered escape at that point. Now, and that creates all kinds of fun things, which we'll just show you in a few minutes here. So the interesting thing with the Growl engine is that the escape analysis is actually much better in the sense that you can do that once, and it's going to say, okay, I think it's still locally contained, so I'm going to consider that it passed escape analysis, right? If you do it twice, then it will fail. So if I go method call with it, right, then it's possible that, well, if you do it twice with Growl, then it's going to fail escape analysis. If you only do it once, then it's going to pass, as long as the data remains locally scoped. And that's an issue, because has anyone ever seen like a talk like your profiler is lying to you? Excellent. We're going to actually catch we're going to catch the profiler with its fingers in the cookie jar, saying, no, my fingers are not in the cookie jar. So let's go and have some fun with that. Any questions before we start this? Because I think the next slide is, what is the next slide? Oh. Is that one, the one you like to see, right? Because that means end beer time. Yeah, that's another view of our Cretan adventure. So just to say, it's a great place for a conference, I think. Okay, let's see if we can have some fun here. I got all kinds of, oh yeah, we have some code. And you can't see it, right? Because I need to, why did it not do that? Arrangement, mirror, awesome. And of course we gone to the wrong, can we do that? Okay, I don't need to do that. Okay, fantastic. Did I hit the right one? Oh yeah, look at that. Okay, so here we have all kinds of code, and we actually have this, you know what, I'll just run this whole thing. Oops. Nah, just try that one. Okay, here we go. Oops, I probably not should have started that. What did I do? Oh, okay, got lucky, started the right one. Okay, so what is this thing here? Has anyone played the Mastermind game? Oh, I forgot. Let's turn Wi-Fi off. I had somebody trying to, I think I had my wife trying to Skype me in the middle of one talk, so this pops up, oh, damn, Wi-Fi off. It was really fun. Then I had to explain to her why I couldn't take her call, right? We know how that goes. Yeah, so, okay, so this is sort of like a very crude simulation of Mastermind. Anybody know this game? Like the, pick colors, you guess and score guesses and then refine guesses based on score type thing. So in this case, I just use numbers instead of colors because it's just easier. And let's just put some stuff. Actually, no, I don't want to do that. Let's forget that. Cancel. Actually, I do want to close that. I want that one. We'll just do it this way. So anyways, so the question is, so basically what I did was I said, okay, go looking for this particular number. So this is, so it's off running here, burning CPU at 100%, and we're actually, and it's found the answer right here. So basically it took 13 seconds to figure out that was the number combination that I actually gave it. Okay? So it's a pretty simple program. So the question is now, if we want it to go faster, we want to get to this answer faster, how are we going to tune this? I'll give you a hint. It's a talk about memory. Sorry. You can say? Okay. Well, in this case, what I want to do is I want to actually, let's launch my handy-dandy GC log analysis tool. So what I want to actually do is I turn on GC logging, and let's see where the GC log ended up at. Presentations. Oh, I love it. Okay, down here. There we are. So there's a GC log. If you want to see what it looks like, it's like kind of ugly stuff. Just a whole bunch of data about what it's not a trail of what the garbage collector has actually been doing. So let's just load it up in here. And yeah, it's only run for a minute, so it's not really all that great. But so the question is, okay, so what are we looking for? Well, I'm going to look at application throughput. Here, let me just make this smaller so I can make it bigger. Make it a little easier for everyone to see, especially in the back. Okay, is that good? Everybody happy here? Cool. And you can see that my application throughput is 99.8%. So that means it's spending, well, 226 milliseconds of time garbage collecting out of a runtime of 1 minute and 35 seconds, right? So it's not really a lot of time. You can see how often it's run. So, you know, you can look at this and say, like, you know, if I got rid of all garbage collection here, this thing's probably gonna run 200 milliseconds faster, right? On 13 seconds, we don't care. That's nothing to be concerned about. But if we actually go down into where we know the problem is, because it's a talk about allocation rates, there, how does that look? Isn't that fun? Sorry? Oh, the chart does? Okay. So we're looking at the allocation rate there. So how many megabytes per second of memory am I actually consuming in this particular application? And you can see when we finally get into something which I'll call steady state, we're running probably around somewhere between 2.5, 3 gigabytes per second. What's our magic number? 0. No, that's our dream number, right? Okay. Yeah, our magic number is about 1 gig per second, like above the threshold. We know that we should be able to get some really good performance improvements by reducing the overall allocation rate here. Okay. As a bonus question, right? For that, for the extra beer. Did you get the extra beer for? Awesome. Okay. Yeah. Normally I come with presents, and unfortunately that didn't happen this time, so I'm sorry. But actually, we'll give you presents. This is our GC analysis tool. If you want licenses to it, just send me an email, say you're here. I get you a free license. Okay? So the whole thing is, anybody have an idea why the bonus question is why the allocation rate goes from sort of like in that shape?
The VM's warmed up, so all of your code's jitted, and now you're just in the same kind of loops over and over again?
I'll be nice tonight. Close enough. Had to think about it for a second. Normally I'm not nice, but you know, we'll just say I'm feeling kind of nice tonight because I got rained on or something. Okay. It's along those lines. The code is actually getting jitted, but actually what we're seeing in this whole thing is that there are allocation sites being actually removed by the code by the JIT. And so as the allocation sites are being removed, then of course we do get some nice reduction in the overall allocation rate. So that's good. That's good news for us. It's kind of helpful, I think. Okay, so now the question is, okay, so we know we have a hot allocating application. We want to reduce the allocation sites in the spirit of using what I call poor tools and cheap drink. I'm going to use Visual VM, which is just a open source tool platform. Well, it's a container for performance tools. And what I'm going to do is I'm just going to attach it to our mastermind code. I'm going to go to a profiler, and I'm going to go to memory settings here. And sorry, I'll just make this a little big so you can see what's going on. So the first thing, whenever you use a profiler, make sure that you know what your filter sets look like. For execution profiling, they tend to look something like that. In this case, do you know what the effect of this particular filter is?
It only profiles code in that path.
Bingo, which means the net effect is that it basically filters the bottleneck out of the profile. Have fun. Right? It's like if you don't know what you're looking for, you may not find it, as they say. So anyways, in here, we just want to make sure that your filters are all set up properly and everything like that. So in this case, they are. So we can just attach. And again, I'll make this smaller so we can make this bigger for everyone in the back. Get rid of this thing here. Now, so here's the most bizarre thing that you can think of, right? Okay, so we're talking about allocation rates, which is a frequency thing. And you think about it, okay, what's an execution profiler? Well, an execution profiler is a frequency measuring thing, right? So you would expect that hot allocation site should be picked up by the execution profiler. Sometimes they are. Most of the times they're not. And even when they are, they present you with like a really confusing view of what's going on. So if I'm dealing with a known memory problem, I'm going to pull out a memory profiler. However, when I configure it, I'm going to look at it, this is a frequency problem, so which means I'm going to sort this whole thing by allocated objects. Okay? So this is the rate at which we're allocating objects at this point in time. Or, well, it's a one-off of that, which is good enough. Okay, so we can go back to our lovely, wonderful demo application here. And I can just clear it out here, and we can run the test and watch the profile. And this is the fun part, right? Because, you know, I'm working, but I can do nothing at the same time. I got a couple of days of this coming up. That's really fun. Right. So does anyone see the hot allocating object? A score. A score. A score. Awesome. So let's do a snapshot. Where's the snapshot? Oh yeah, there it is. Okay, so let's get a snapshot. And you can see, well, there's two things up there. There's an int array in terms of live bytes, but I don't really care about live bytes. I care about frequency. So when I, again, sort on frequency, sorry guys, I make it big for you again, you can see that score comes up right on top there. Isn't it lovely? Just as planned. And so you can just go down here and say, okay, that's my hot allocation path, right? So that's my vector into the code. And so, of course, we would like to look at this thing here. That's my allocation site, yeah? Okay, and that's in this method here, which is board is possible solution. So without further ado, oh, see, I did get caught by somebody there's messaging me. Wonder who that was. Yeah, I have to tell you, it's like kind of funny. Since I went down to Best Buy at the last minute, I almost got caught I did get caught in the rainstorm, which means I was, even though I was here all day, almost late for this talk. As my wife would say, only I could do something like that, but there we are. Okay, so let's just terminate this and close off that and that. And okay, so here we go. Is possible solution. Anybody see the bad boy there?
You're allocating an object inside of the loop.
I'm allocating an object inside a loop, right? Nasty, nasty, nasty. This is something that we shouldn't actually be doing, right? So, let's do a little bit of analysis of the situation to see what's actually really going on here. So what is the scope of this particular piece of data? Pretty much local to the loop, yeah? Okay. Should it pass escape analysis? Well, if it's local to the loop, it should pass escape analysis, right? Okay, that's cool. Let's see what this thing looks like. So it's 2 ints and a bool. So I think that qualifies as small, don't you? So really, shouldn't this thing be allocated on the stack? You would think this would be a good candidate for being stack allocated. Yeah? Okay. Okay, so what's up with that? So what I did was I actually said, okay, JIT, why are you not allocating this thing on the stack? So I set a whole bunch of other command line flags, and I got like another set of logs set up, and I used this wonderful tool written by Chris Newland, who actually was inspired to write this tool at jcreate. So I probably should not be rubbing that into the guys anymore, but okay. So and somewhere, I've actually done the work of actually loading all of this up into JITwatch. So it's a project within the Adopt family of projects. So you can go there on GitHub and just find it and download it if you're interested. It comes with wonderful instructions and tutorials put together by Chris. He's done a fantastic job. Is that big enough to see in the back there? We okay? I can make it smaller so it's bigger if you want, but I think it should be okay. Okay, and so what it does is it basically says, JIT, what have you been doing? And this thing like sucks it all up into, if you read the log, you're going to want to poke your eyes out. It's iReadable for some definition of readable. Okay, Anyways, and so this thing actually comes up and says, okay, well, here's all my allocation sites that have actually been eliminated. And there's 143 allocation sites that have been eliminated by the code. So if we go com.code work, boom, baby. What do we see? Isn't that cool? The score is being eliminated. That allocation site is being eliminated. Okay. So now we get a problem because the profiler tells us that's a hot allocation site, and JITwatch and the compiler are telling us like, nah, I get rid of that allocation site. Does anyone see what's going on here? I got some shaking in the back there. What's going on? Sorry? Oh, you can't see the, so you're trying to adjust your glasses. Sorry? The profiler is lying. Yeah, I told you that was going to happen, right? We caught fingers in the cookie jar. Okay, so how's the profiler lying in this case? Well, what the profiler is actually going to do is it's going to go into the runtime, and it's going to do this wonderful thing called bytecode injection. Have you heard of this term? Okay. And the bytecode injection is actually going to wrap the allocation site in a call that passes the allocated object into a method defined by the profiler. And what does that do? Breaks escape analysis. So all of a sudden it fails escape analysis. And now the object is now reported as being a hot allocating object. So we can go and do the reasonable thing, which is to remove the allocation site out of the loop and hit a reset and all that wonderful stuff. Guess how much in performance you're going to, guess what the performance improvement is that you're going to see on this thing? Practically zero. Practically zero. It actually might even run slower. Okay? In some cases we actually see it runs in a second longer or something like that, or half a second, depends on the data set we actually use. So, I think what we can all take away from this is that there's really a regime that we followed here. The regime we followed in this whole thing is that, I'll stay here to make your life easier. The regime that we followed here is really that, first, I used the garbage collection log because the garbage collection frequencies and pool sizes and the allocation, the information that it has about the memory pool occupancies gives me enough information that I can estimate allocation rates. Okay? And with the estimation of the allocation rates, I can see that I have a hot allocating application. At that time, I can put the profiler on it, but I'm also going to use the JIT compiler information to actually confirm what it is that I'm actually seeing. In other words, if I suspect that the JIT should be taking out this allocation site, I'm going to confirm that by having the JIT actually report on what it's doing and then load that up into something that I can actually see exactly what's going on. Really, the hot allocation that's happening is actually the int array. That's really the bigger problem in this particular application, but that's masked by the score object being allocated so frequently when the profiler is attached. Okay, and then after that, of course, I can use the profiler to narrow in on the piece of code that I want to modify. I'll make the change, and of course retest to see if it made any difference in the performance. In other words, did we get it? Did we find the right spot or not? And that's pretty much all there is to it. 20 after 8, so that's about an hour too, isn't it? So we're about right on time. Cool. So with that, I would just flip over to my lovely questions slide and ask anyone if they have any questions. Or, yes, sir.
As someone who's never done anything performance tuning related before, can you explain what you meant earlier when you mentioned what do you mean when you say transactional or a transaction?
So he's asking, as someone who's never done any performance tuning before, what do I mean by a transaction? In this case, I probably just mean it's sort of an abstract concept, meaning it's some sort of business transaction, not a database transaction. So it's some stimulus coming from the user to some end result, actually coming back to the user. Or, you know, in some cases, it's basically stimulating an API. How long do I get a response? So it's a latency measure. And on one hand, on the other hand, it's like how many of these can I do per second, right? Before I saturate some part of the system and I simply can't go any faster. Yes, sir.
How do you place it if you turn off the logging within advanced section of the system?
Ah, fantastic. That's an entirely different, actually I do a 4-day talk on that. The question, yes, sorry, yeah, thanks for reminding me. What was the question? So how do you trace things if you don't actually do any logging? And that's a seriously deep question. And like I said, I've had this discussion even with the Log4j guys in the room, so it was kind of fun. There's a book, maybe you can publish this wherever you publish it, written by Sebastian Daschner. It's like modern JE applications, if there is such a thing. But he does have a performance section in there where basically he said, can you review this? And in the space of a couple of hours, I completely destroyed the chapter. And so he had to rewrite it. And he did a reasonable explanation of basically how you can trace applications, well, not necessarily trace applications, but understand what's going on inside an application without using frameworks like Log4j. The first thing you have to do is you have to figure out, okay, what am I doing? It's like Log4j, things like that, are really there for understanding when something bad happens. So you have some sort of error in the system, right? And the question is like, how frequently do you actually get errors in your system? You may not want to answer that, but that's a question it's more of a rhetorical question. So generally not very often. So other than that, the question is, what are you doing? Well, a lot of times what you're doing is you're actually creating audit trails or like what I call transaction logs and things like that. So you can actually do a trace like that. And the logging frameworks are just notoriously bad for that type of activity. It's really, if you're journaling something, you really want to use a journaling solution. And a good journaling solution would be something like Chronicle, written by Peter Lowry, right? This is a framework that's actually used in high-frequency trading applications. If you know anything about high-frequency trading applications, the ICE guys should anyways, the last thing you want to do is go slow, because this is first past the post, right? You go home with the gold or you go home crying. That's about it. So you don't want anything to get in the way of that, which means that you need to find unobtrusive ways of figuring out what's gone wrong, right? So, there's regulatory concerns. that you have, that means that you have to build these transaction logs and things like that for HFTs. So they need these types of things. So these tools are actually built to work at the speed of hardware. Log4j certainly isn't in this particular case. And again, it's a perfectly okay thing if you just want to record errors. But if you're doing audit trails or transactional logs or things like that for tracing, then you want to use the appropriate tooling for that. And I say Chronicle is one example of that particular thing. The other thing too is that, and this is part of what we call a methodology change, or actually what I call the development of methodology and performance tuning, is how do you actually get to root cause without actually monitoring anything? Okay, and we actually have ways of doing that. That's our machine learning engine actually implements this thing, right? Since we don't know what your performance problem is going to be, like there's infinite ways that things can break. We can't possibly train a machine learning algorithm to find these things. So we actually have to find a different way of doing it, which basically means we've tilted the problem on its side and we look at it and we've converted it from an infinite space to a finite space. As soon as we have a finite space, then we have a chance of solving it, right? So the methodology actually comes up with a taxonomy for every performance problem you're going to encounter, or the root cause of every performance problem you're going to encounter, or at least we like to think it does. So far it's been working fairly well. And in those cases, logs are generally useful. I would say generally logs are not useful in their present form. I mean, the first chart that I put up there should have showed that, right? It's like, how often do you actually use the logs to find a performance regression in your system? Because my answer is never. I never look at anybody's logs for performance regressions. I'm really interested in what's happening here and now, because that's where you're going to find the problem. It's in the here and now, not what happened last week or last month or whenever. Okay, so the methodology that we actually teach and we use actually prescribes how you can actually navigate through this taxonomy to figure out root cause without actually having any direct monitoring on the application, right? That's not to say there's not needs for audit trails and things like that, but I consider that to be a completely different problem with different solutions. Yes, sir?
Did you say the profiler is still the best place to start if you're trying to identify object churn?
Churn? Okay, once you know that you have an object churn issue, then yeah, I would go to a memory profiler, but again, use it with care. But absolutely, any memory profiler, your flavor is going to give you good information on this problem, assuming that you've studied the JIT to understand which allocations are going to be eliminated and which ones are not going to be eliminated. Quite frankly, most of the issues we find have to do with logging. Logging is probably the number one cause of memory churn in any of the applications that we dealt with. Certainly, we've had experiments where we stripped all of the logging out of an application and just deployed it that way with, to really fun effect, So the thing about how with the modernization of the APIs within the logging frameworks, you can actually get most of the way by actually using Lambda forms in your log. So at least you get what I call lazy initialization of some of the parameters. But essentially, you're still reduced to writing guard code. And if you have to write a lot of guard code, then to me, that's a code smell. That's like your API is broken. If you have to guard yourself from using an API, the API is broken. Yes?
Let's say that I have an application and I fix whatever magical memory problem is in it.
Right.
How should I go about writing some sort of CI test or CI check to make sure that that memory issue is not reintroduced later or in some other form?
That's actually a really good question. So we've actually created a product for Swiss Rail because they do this regularly. And so they have probably the best test system on the planet. Basically, their test system becomes production every 6 months, and their production system becomes test at the same time. So they just go to a router and fix the routing tables, and off it goes. And since they're dealing with trains, and they have to know where every train is in the country, and they update the train schedules like every 10 seconds or something like that, and it is a train, and they sort of do want to know where they are, they take their testing very seriously. So one of the things that they actually do is so we built them something that actually consumes the GC logs from their test environment, and they feed that into Mercury, and then they do some analysis using the Mercury QuickBooks type solution. We do a lot of analysis ourselves up front, so we look for things like heap stability factors and things like that. These are all metrics that we've developed on ourselves, because if you're going to tune 3,000 or 4,000 JVMs in a year, you're going to have some tricks up your sleeve. Otherwise, it's going to take you a very long time. Okay, so that's pretty much what they do. So it really comes in, can you put something like this into your test environment? The other thing is your test environment complete and realistic? I mean, Swiss Rail, I trusted. I would actually tune the garbage collectors in Swiss Rail's test environment. There is no other production environment that I've worked with that I actually would bother to test, to tune the collectors in a test environment. The collectors and how memory works is so sensitive to the load that if you have any perturbations in the load, any tuning you do is probably going to fail by the time you move it to production anyways. Okay, any questions there? Yeah.
So you mentioned that most of the performance issues are related to logging problem.
Yes, most of the performance issues are related to logging in our experience.
Yeah.
Your mileage may vary.
Yeah, and at the same time, some of the related, regulatory reasons or whatever, we need to log into the system. So do you have any?
Well, that's what I'm saying is that you don't need to log into the system.
Yeah.
If you need to audit, that's one thing. Okay, but the auditing tools tend to be very light have a light touch on memory footprint, which the logging tools do not. They tend to generate a lot of memory churn. And I understand that you probably don't have access to the to our tooling and stuff like that right now. It's very difficult for you to actually take that and deploy that into your system. But really what we're saying is that if you look at the future of performance regression analysis, you have to recognize that, if I showed you a chart of Twitter services right now, like all 160,000, how they're all interconnected, you're gonna probably do what the Twitter guys did, was just throw their hands up and say, we give up. We have no idea how to manage this anymore. So which means the obvious solution is to, since we're beyond human scalability, is to start having machines manage the machines, which means the machines have to do the diagnostics, right? Which is why we built the diagnostic engine in the first place, is to have the machines monitoring the machines. And the ultimate dream down the road is to actually try to implement some self-healing in the process.
We're going to hold off on questions for now. So
Sure.
If you have any additional questions, please come see Kirk, but we have an announcement.
Yeah, so first of all, let's give a big round of applause for Kirk.
Thanks, guys. Great audience.